If a set contains a zero vector, it's linearly dependent. True or false? True. Yeah. Any set with a zero vector in it is linearly dependent. A set of vectors is called blankety blank if the vector equation, that homogeneous equation there, has only the trivial solution. Yeah, linearly independent. And a linear transformation is a special kind of what? No. No. Anybody read 1.8? I adapted it from your question. Yeah.
Well, my question was just
yeah.
Function.
Yeah. Special kind of function. All right. All right, so don't forget, for your quizzes, you give yourself a score from 0 to 4, point for each question, a point for writing a question, and a point for taking notes if you did. So maximum of 4. Record your score on your folder and put your quizzes, your completed quizzes, in the folder. I keep them on file. So I emptied them this morning, and I can't remember which table. One table had no quizzes in there. So I think you might have just forgot. Yep. All right, so you may notice my demo portion of the lecture, I do not go through the point by point from the section of the reading, like this is the definition, these are the theorems. So like this demo is going to be very short. It's going to demonstrate the use of the 3 theorems and the definition that are in the reading, but I at no point like write them out for you. So that's on you to do the reading and have written it in your notes if you want it written in your notes. Also on Moodle, there are my notes from the reading if you want to use those to sort of help you summarize. All right, so in this lesson, we're going to study the concepts of linear independence and dependence of a set of vectors. So in the reading, there were 3 theorems that help you identify linearly dependent sets. So let's briefly review, just verbally, easy ways to identify a linearly independent set. There's 3 of them. Anybody remember? Dependent. An easy way to identify a linearly dependent set. If it has the 0 vector in it. Okay, so of these sets, do any of them contain the 0 vector? U, yes. So U is definitely linearly dependent. So 4 of these 5 you can identify as linearly dependent without having to really do any math, right? We can use some of the theorems from the book. So U is linearly dependent because the 0 vector is an element of the set. Zeros in there, meaning a vector full of zeros. We are linearly dependent. All right, what's another way of being able to identify linear dependence? Yeah, if one vector is a multiple of another. So do we have any of those up there? R, yeah. So the third vector in R is a multiple of the first vector in R. So we'll say R is linearly dependent because 306 is 3 times 102. One vector is a multiple of another. All right, what's another way? More vectors than entries. How any of the sets have that property? S. More vectors than entries. All right, and the last theorem was that if some vector is a linear combination of the others, if any vector in the set can be written as a linear combination of any other vectors in the set, then it's dependent. So what do you think? Any V? Yeah, because the third vector is actually the sum of the first two. So you put weights of 1 on the first two vectors, you get the third vector. So the third is a linear combination of the first two. So yep, R is a special case of that, because in R you could put a 0 weight on the 460, a 3 weight on the 102, and so 306 is a linear combination. Yep. So V is linearly dependent because 3811 is 1 times 222 plus 1 times 169. So it's a linear combination of some other vectors in the set. So those are our 3 ways. So I say 3 ways because, like Justin just pointed out, this one and this one are really the same. And then the other 2 are the 0 vector and more vectors than entries. All right, so those are theorems, and we can talk about why each one creates a linearly dependent set. But first we need to talk about what the definition of linear dependence is, right? Once we know that, we can see why these work. So the last setup here is T. 3 vectors in T. There is no obvious answer of is it dependent. You can't immediately tell just by looking at it. So I have to do something more, do something a little extra to determine whether or not this is independent or dependent. So to do that, I'm going to use the definition. Okay, so I'm going to use the definition of linear independence to determine if this is independent or dependent. So the definition from your reading and from your quiz said that if you take a vector equation, x1, v1 plus blah, 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 xp, vp equals 0. Right? So this is a vector equation. All the x's are just unknown weights, right? The v's are the 3 vectors in the set T, and the 0 vector is just the 0, 0, 0. It's a column of zeros. So if this has only the trivial solution, what is the trivial solution again? What does that mean? All the weights are 0. Yep. All the weights are 0. Okay. Then the set is linearly independent, right? Otherwise dependent. So I'm going to solve this vector equation with our 3 vectors. So really what I'm trying to set up is my weights x1, my first vector in that set is 2044 plus x2 times the next vector is 0101 plus x3 0011. I want to set that equal to the 0 vector, which all my vectors here have 4 entries, so I have a 4 entry 0 vector. How do I solve this thing? I'm going to make an augmented matrix and row reduce it. So my matrix, these are going to be the columns. So I have 2, 0, 4, 4, 0, 1, 0, 1, 0, 0, 1, 1. Augment with the right side, 0, 0, 0, 0. Row reduce. And at this point, you can use technology. And we get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0. All right, so this says x1 is 0, x2 is 0, x3 is 0. So that's the trivial solution, right? Are there any other solutions? No. In order for there to be other solutions, to have more than one solution, you'd have to have a free variable in there somewhere, right? So I have no free variables. I have only the trivial solution. So this is linearly independent. Only the trivial solution means the set is linearly independent. So no free variables, because in order to have multiple solutions, you'd have to have a free variable somewhere. And to have a free variable, you would have to have a column without a pivot, right? Because that's the definition of a free variable. It's the column without a pivot. So when you have a pivot in every column, you can conclude linear independence. Yes. Yeah, yeah. Well, when you started, I don't see a triangular matrix. Oh, because it's already an upper triangular. Yes, you could rearrange and see that it was, there's a pivot in every column. Good, yeah. Great. All right, so now, knowing the definition of linear independence, those three methods of quickly determining linear dependence, the zero vector, if that's in there, you can use any weights you want, right? You could put weights on, you could put a weight of 18 on the zero vector and it would still be all zeros. So that's why the zero vector one is easy, because no matter what weight you put on it, you'll still get zeros. And then one is a linear combination of the others or of some others. That means that I could manipulate the x2 and x3 weights, say, to make them add up to 0, right? So that I could still get the zero vector without having 0 weights if one's a multiple of the other. And then, oh, more vectors than entries. So let's look at S, right? You could easily put a 0 weight on one of these, and then you could find some weight x1 and x2 to put on two of these to make the third one. Yeah, anytime you have more vectors than entries. All right, so that's my lesson on linear independence and dependence, and you have some activities.